So I'm here talking to Alex about our new product offering. We're here in the Quantum Design booth, which is our sales partner. Lakeshore is an Ohio-based company, and we have our M81 synchronous source measure system. This is a product we've been selling now actively for about 2 years. And yesterday, for the first time, we introduced the world's first DC-AC lock-in SMU, which we have 2 examples here, wired to a device within our cryogenic probe station. Cryogenic probe station is used typically in research, but increasingly in applied applications for nano device characterization, because it can take temperatures down to base of below 4 Kelvin, all the way up to 400 Kelvin, which allows researchers to easily collect characteristic curves, voltage, current, and temperature as well, which is useful on many materials, particularly advanced semiconductors. So Lakeshore is leveraging its deep expertise in ultra-cold temperature sensing, ultra-cold sensor measurements in a general purpose instrument that is useful for IV characterization, both DC signals, AC signals, and with lock-in detection. Lock-ins, for example, avoid offset voltages, avoid unwanted frequencies and unwanted signals, particularly important when devices get smaller and smaller, whether they're traditional devices or emerging nano-based devices. Moore's law continues. At some point, silicon will be replaced by more advanced technologies, including nano and two-dimensional materials such as graphene and layered graphene and other types of exotic materials. These voltages and currents are getting smaller and smaller as time goes on. We know the voltages have dropped lower, 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 and these products have nanovolt sensitivities, femtoamp sensitivities. We can support up to 3 channels, now 3 SMU channels. We have some other modules that do voltage current measurements, sourcing and measuring. Along with our probe stations, we offer cryostats. This instrument can work with anybody's prober, room temperature probers, high-speed probers, room temperature, high, low temperature, high speed, any test fixture that you'd like. You know, there's some projections out there that talk about nano devices kind of taking over and growing dramatically into the mainstream, replacing some silicon for photonics applications, very high speed, very specialized applications. As devices continue to shrink, noise becomes an increasing problem. So voltages are going lower, power, heating is a problem. So for sure, integrated circuits and transistors that they're made of are shrinking, shrinking, shrinking. As we transition to atomic and nanoscale building blocks, transistors, that only accelerates. So the signal levels continue to drop and may accelerate and start dropping. As your signal levels drop, noise is more of a problem, thermal offsets are more of a problem. You need some advanced measurement techniques to get rid of those issues and still give you good fidelity of your signal. We've been using both DC and AC measurement techniques. This system incorporates capabilities to both source and measure, DC and AC. I mentioned lock-in, and phase information is available. And now we bring that technology to the lock-in 4 instruments in 1 architecture. So you can source voltage and currents, user selectable with the front panel or the remote program, and you can measure voltage and current or any of those combinations. Here's an example. We've architected this system for the lowest possible source noise and the highest possible sensitivity both. So when you're making low-level measurements, you have to worry about the noise of your source and the sensitivity of your detector both. Having one or the other, but not both, is problematic. Here's an example of a very low noise DC SMU module, SMU instrument, versus our SMU instrument. And you can see the thickness of the blue line versus the thickness of the red line is roughly 100 times lower noise. And this is 0 to 20 megahertz. So this is so-called wideband noise. And you can also see our SMU putting out a AC sine wave that we can run a lock-in detection on. User can pick frequency and amplitude and measure X and Y, phase angle, and multiple harmonics, which DC SMUs cannot do, ignoring signals that are unwanted, as well as DC offsets are rejected and ignored. And our measurement is at the red line here. So both our source and our measure noise performance is many orders of magnitude, many multiples less than what's out there. And we think this supports we built this for our applications. We built it for future applications where the signal levels are going to continue to drop, have been and will continue to drop significantly lower. So